Okay, today I bring you Robert Collins with NTFS Isn't Really That Bad.
Thank you for coming to listen to my tale. I hope you enjoy it. We're going to talk about a 10 times performance improvement in Rustup on Windows. Well, mostly on Windows. Before I get into this, who here doesn't know what Rustup is? Okay, I should probably put my hand down. So, at any point during this talk, questions are fine. I don't want to leave anyone behind. If you don't understand the rest of the talk, that's going to be pretty disappointing. But if I ask you to wait to the end or come and talk to me later, please respect that. There's a lot of people in the room. Discussions, definitely, they can wait. I do value the feedback, but there's 100 or so people that'll be processing whatever discussion we have, rather than just you and me. Come and see me after the talk. Now, there were a lot of hands that came up when I asked about Rustup. And excuse me for 1 second. The beard is not where it was last year when I presented. Rustup is the language-specific installer for Rust. So if you're not getting Rust from your Linux distribution, you get Rust from Rustup. So it knows how to install Rust and the various Rust components, and it knows how to install it on Linux and Mac and Windows, and potentially some other weirder things in the future. So about a year ago, I was on a road trip. I was very, very far away from my workstation, and I was using this Surface. I was in a horrid, horrid little motel with very, very terrible Wi-Fi, and the 4G network there was even worse. And Rustlang, installed through Rustup, installed excruciatingly slowly. And I wanted to work on some Rust code. I wanted to work on my personal project, but I got curious. What was up with that? So I go looking, I Google it, and I find a bug. It turns out that installing one particular part of it was really where the slowness was, installing the documentation. There's a bug report. Clearly, the problem is solved. And the bug report correctly blames the antivirus on the system. I don't need to do anything else. Turn the antivirus off. Hey, hang on. Why is the bug still open? So turn the antivirus off and it's still slow. There must be something more to it. So a bunch of knowledgeable people got into a very long discussion on that bug and in a few other places about what the problem was. And they got out tools and they measured it. What is common about these different measurements? No, the bottom one's not on Windows. And in fact, Rustup runs on all the platforms. None of them exercise NTFS very well. They also don't exercise NFS very well, or GlusterFS, or CephFS. In fact, the only one that really performs really well on SSDs is tar. And why? If you know the answer why, you've probably got the rest of this talk. Great. Some of the other talks are very interesting. But there's a little bit more to it. And the bug had gone off the rails. I'm sure you've never seen a bug where people are arguing about the wrong thing. NTFS is terrible. It can't be fixed. We are going to have to change what we're doing. Users don't want docs. Let's not ship them. Everyone Googles it, except when they're on a plane. That's actually changing, but not everywhere. Let's ship them in an ISO file or a zip file and run a local web server. I contributed to some of these discussions, and I feel bad about that now. One of the more interesting ideas is let's, unpack them when the user asks for it. So we'll make the user wait when they actually want to look at the documentation. Hang on, I'm not entirely sure we're winning. I ran into another bug in the bug tracker, though, that said disk access is slow during install on all platforms. It's like, hang on, there's something going along here. And that got me writing some code, at which point things start to get better. So when I started, the whole installation process was about 4 minutes. And that was with the downloads cached, and there's a little bit of a horror story about that I'll get to in a second. But 3 minutes 45 seconds to install the compiler, the libraries, and the documentation down to 2 minutes 23. So that was a pretty big win. And it certainly helped with my battery life. But this patch is doing a very, very, very small conceptual change. Instead of a copy, when we've finished processing the data around a particular module inside the Rust components, we're doing a move. Tiny change. Dramatic win. Of course, by this point, the Rust project I wanted to work on, which is one I'd started about 2 years before, when I'd been between jobs and was really quite interesting to me, is completely forgotten. I have no idea what's going on with it. I'm just figuring out what's going on with Rustup. I'm installing and uninstalling, installing and uninstalling, tracing it. There's a tool, Process Monitor on Windows, that's very similar to Strace, except it's got a GUI, which makes it harder to copy the results out, harder to look at it. But it does have a log file format that is machine readable. So pluses and minuses. Rustup itself, though, helpfully wasn't built with performance optimization in mind. So there's no way to tell it, skip downloading and don't delete the files that you've downloaded when you're finished. So every single time, while it was downloading the files and then it started installing them, I would copy the files that it had downloaded out of its cache area while it was installing them. And then when it was about to start downloading, I'd copy them back in again. So that I was avoiding all the network I/O on this thing. Yes, that would have been an obvious thing to fix, but it's not the thing I was thinking about. I still haven't fixed it. It turns out that opening a term info database that doesn't exist takes a certain amount of time. And if you don't treat this as a part of global state and replication and you keep reopening it, you're going to spend time opening it and opening it and opening it. I don't know exactly how much this saved, but it certainly made the traces a lot easier to read if between every single file that was being output there wasn't a bunch of stats for non-existent files opening a term info database that doesn't exist. Because Windows has a syscall to get term information rather than files on disk. Rust, it's a programming language, completely able to manage global state. Rustup, a tool that started off as a collection of shell scripts and was turned into Rust when it got too hard to write it in Bash. It's not the best Rust in the world. I'm in a position to say this because when you go and criticize it, you'll be criticizing the team, which I'm now a member of, so I'm not punching down. Punching sideways, maybe? So the next thing when I was looking at the traces is that every single time we extracted a file, we statted the directory above the file to make sure it still existed. This is very defensive programming, and it took about 2 seconds. Just let that sit for a second. 2 seconds of the total runtime was just spent doing a stat for a directory that already existed. And it's not that the stat was implemented badly on this platform, it's just the time it took to do a stat. I've seen this on Linux as well when I was working on BZR. Stat isn't free. I'm going to pop back for a second, actually. Yes, so the number I wanted to mention here that I skipped over is that was 20,000 stats that we saved. It adds up. Then I started looking for other wins without kind of tackling the really big elephant that is going to come along later. There's I/O contention that I could measure because we were reading from a tar file on disk and then we were going and writing a bunch of files out and then we were reading from a tar file on disk and we were writing a bunch of files out. We ended up with I/O contention. I'm sorry about this huge wall of text. I actually skipped about half of the commit message to do this, but did I manage to get it in here? Is it going to let me? Yeah, between 0 and 12 seconds, depending on exactly what the system was doing, just by having a slightly larger buffer size that we read into. Now, having large buffers is an anti-pattern, having no buffer is also an anti-pattern. And the interesting thing about Rust is I had to go and do this in another place. When we hash the files that we've downloaded after we write them to disk, and we hash them after we've downloaded them to disk because they might already be on disk because we've been interrupted. So it kind of makes sense to just get them down to disk and then hash them all. Rust's built-in buffer size is 8K. The minimum amount of I/O you can do is 4K, so this isn't really a terribly bad idea, but the amount of I/O the kernel's going to happily dispatch for you is rather larger than that. So you're not exactly optimal. And I looked at submitting a patch for this to make it larger. This is actually placed on the stack in a lot of places in the Rust standard library. So when you make this buffer larger, the standard library fails to build and self-test. So I couldn't actually make that work. But 12 seconds on that 2-minute 25 that I got it down to. Is anyone keeping track what we're down to? There will be a test. Okay. Another 4 to 6 seconds with a 1-line patch. This one was quite nice. Do you remember the bug report I started with? Starts has this kind of picture at the top of it. So this is from that process monitor tool I mentioned, and they helpfully put a screenshot of it rather than copying some of the data in text format that people could, work with. This is the same thing annotated up. So the 1 is stacking the file to see if it exists. Don't want to write to a file that exists. That would be a bug in the tar-rs library. We'll come back to that. Then we open the file, write the data, and close the file. Then we open the file, set the M time on the file, and close the file. Then we stat the file, read the permission data from the file, and then we close it. And then we open the file, set the permission data on the file, and close the file. And then later on, way outside the context of the snippet, we read all the files in the directory and set the permissions on them again. I can now say, I can't say this now, but at that time I could say, hey, I didn't write it. But I was trying to figure out why it was slow and which parts of how it was written made it slow and what do we need to change. So the 1-line change was just this. We don't care about M time. Turn it off. Saves this open, read, write, and close. And you might say, well, why do we have to do an open, read, write, and close? Isn't there a syscall that just sets your M time on a file? The NT kernel doesn't have an M time call, whatever the actual syscall is, and I didn't look them up for this talk, I'm sorry, I was too busy trying to provide an entertaining experience. But what it does instead is have a small surface area, so people are hooking in, they have one code path to go through and do things. In Linux, we have lots of different ways to do the same thing, and it's a different set of trade-offs. You can make things very, very fast and very optimized, but it's harder to audit. The underlying data structures are completely approachable and able to do the same operation with roughly the same efficiency. It's not an inode, it's stored in the master file table. But the real killer is you're doing 4 kernel mode transitions. When you've got 20,000 files, that adds up. So we save 4 to 6 seconds by, and in this case, because we're installing documentation that people are going to read, we don't care when it was edited. Do you need to back it up? Install it again. It's easy. 4 to 6 seconds, just like that. The source package is another 7,000 files, and most of the other packages are very large amounts of data, but very small file counts. So these sorts of things don't really matter. One thing that's worth noting is that something like DM delay, if that had been used as a performance test suite to introduce latency around syscalls for folk who are building the lower layer libraries that we built on, they probably would have found these inefficiencies and been unhappy about them way before we got unhappy about them. It really, really, really matters when you build on libraries what those libraries do. And I think the more experienced you get, the more that will matter to you. You may be getting the sense that this is a key part of the talk. It's probably the key slide. This is the pseudocode for what chmod, which has the same problem. There is no file path-based chmod in Linux. And who was it? Was it Alexa? Was talking yesterday about many, I won't say all, many of the security problems in Docker. And most of them related to the fact that it kept opening things by path rather than by inode. And that they are introducing a new OpenApp2 syscall into Linux. And this sort of API that works on paths is the source of that problem because they are racy. There is simply no way to make them secure unless you introduce flags to them that say, don't work if this is something that isn't what it looks like. The open and then operate on the open file and then close it is the secure, race-free implementation under the hood. So what Windows does is actually only surfaces the real core implementation. Of course, then there are compatibility libraries on it that let you use insecure, racy implementations that are also slow. I'll think about that. So I'd reached the point where there really wasn't a lot more that I could do to rust up itself. I had to go and work elsewhere to get improvements that we could pick up and use. So TarRS is a module Alex Crichton maintains. And it's got a number of different users. I couldn't just say, hey, TarRS needs this, sorry, rustup needs this, yo, do it. But I found a number of interesting things there. One was, wearing my security hat, there were some time of check, time of use bugs, which scared me. I don't think we've got them all, but we've stamped it somewhat more firmly than it was. Does anyone not know what a time of check, time of use bug is? Okay, a couple of hands. So it's essentially a race condition where you say, hey, look, does this path not exist? For example, if I'm going to write a file, I might check that there's nothing at that path, and then I can open the file, write to the file, and close the file. But if I'm writing this as, say, root, and someone wants to attack me, if they can create a symlink there pointing off to /etc password, then when I open the file, write to it, I'll actually overwrite etc password. So it opens me up to attacks. And the solution for that one is to use O exclusive. So you make the write atomic. If there's something there, you'll get an error back rather than writing where you didn't expect to write. You move to using open at rather than open. And see the discussion I just had before about Alexa's work. Doing the mode settings, so setting the permissions for both Windows and Linux and BSD, all of which have different APIs for doing this when the file's open. So you want to do fchmod versus chmod. You want to do the same thing with file handles. So actually, I'd say they're all different. I think BSD is the same for chmod, but for file handles, setting the microsecond file times, there was some difference. So that's in the file time library, which then TarRS uses. So I ended up having a stack about 3 deep of patches that we needed to unwind and get merged in. And so there's this interesting final thing, which on Windows, to write the file, you have to open the file in read-write mode, or else the file handle won't be a writable file handle. Doesn't matter what your final permissions will need to be. So you know when you've finished writing the file that it's a writable file. So if you look at your tar metadata and it says the file should be a writable file when you're finished, you don't need to make any syscalls. You're done. Because there's no execute bit either. That's kind of an irrelevancy. It's very, very simple. On Unix, you can open a file yourself for write with permissions on it that say it's read-only. And you can, there's a different discussion. All of these changes that I made TarRS better for Linux as well. Right. I ended up looking at it because Windows was performing very, very poorly. But why weren't people on Linux complaining? They were going, Linux is fine. On my workstation, it installs docs in 4 seconds. What's your problem? Linux and X4 on SSDs are remarkably tolerant of making syscalls to the same path with the same name that you just made a syscall to, the D entry cache and the inode cache. They get high hit rates. It's extraordinarily good. Of course, if you have a workload that manages to run outside the boundaries of those caches for some reason, things get a little bit more complicated. So having good code that doesn't depend on those caches to perform well is actually really useful. See some smiles in the audience. So when I completed those patches, we got that into a release of tar-rs, and we rolled that back up into rustup. There was one additional thing I did, which was I included the handle to the file object that we were unpacking, and it gave that back to rustup. And this let us do a thing where we passed that handle to another thread before we released the reference to it. Now, Rust's memory model is not garbage collected, but it's a kind of much closer to C++'s RAII. So when you get rid of the owner of the thing, not the last reference, when you get rid of the owner, a drop function gets invoked and the thing gets cleaned up. If you want to do reference counting, you put a reference counting layer on top of that, and you can opt into reference counting, but that's a different choice. It becomes a user's choice. So the syscall that all of this Defender work had been turning up in was not read, because we weren't doing a lot of reads. We're just reading from the tar, and it wasn't write, even though it had to scan the content. It wasn't open, it was close. When we closed the file, Defender was slowing things down. So we thought, well, if we close it in a thread, we can make it a lot faster. And we weren't the first people to have this observation. Like Mercurial noticed this. They didn't link it to Defender. They just said, look, on Windows, close handle can be slow. So we'll put our closes in a thread and we'll make things faster. And it works under Python, and it works under Rust. And as I said in the commit message, there are a lot of different reasons that close handle can be slow. And one of the more interesting ones is that the device model for I/O is really fundamentally different than Linux. In Linux, once you've got a dirty page that's been handed off to the file system, it gets put in the page cache, and your application can exit, and it's got no bearing on what the device driver does further down the stack. They're just completely decoupled. You can exhaust the kernel's memory and quit, and haha, fine, everyone else has to suffer. With Windows, question, yes?
I'm just wondering, is there a single thread, and you're basically in queuing?
At this stage, yes. There is a single thread whipping through the tar. The question was, he was wondering, is there a single thread, and I interrupted him. So the larger question is, what's the relationship between the reads and the writes, and how are they all tied together, I think.
I mean for the close, when you're actually handing off to the thread.
So how many threads are closing? Is that the question? Right, okay. So I picked the number of threads on the machine, and there is, so if it's a 4 CPU machine, there's 4 threads doing closes, and there's 1 thread that is reading the tar, uncompressing, doing the writes, the opens, the writes, the make durs, the set chmods, everything, and then handing off just the close handles to 4 threads.
Thanks.
Cool. So the device model for Windows is that dirty page is actually owned by the handle that the I/O is attached to, and if you try and close that handle, because the device driver doesn't own the page, and there's no page cache that's owning the page in the same way, your process isn't allowed to exit, and that close handle call blocks. And other things then can cause this as well, such as filter drivers like Defender, when it's scanning a file just on write, will block you. So as you write down, you say, I'm going to close this file. Even if the I/O is completed, Defender can go, hey, hang on, I'm going to check this first, and you get slowed down. So by pushing those off into threads, we dispatched a lot of work off to both the file system, more work to the file system, more work to the underlying disk drives, and more work to Defender. So my laptop went from being slightly faster and better battery life to trying to melt. The fan here is not that efficient, and I could have fried eggs. So At this point, I was down to 11 seconds to install from that 3 minutes 40 that I started at, which I thought was a pretty good win. Is NTFS really still in the picture? I think we've demonstrated that NTFS can handle small files. Defender is still generating a lot of load. Like, you can see it going right up in the CPU. It's 50-50 Defender and rustup. And we haven't even touched on things like McAfee, Norton, or Kaspersky, other antiviruses, and how they might interact with rustup. And how, going back right at the beginning, how do we actually save a whole minute just by not doing a copy? Is I/O really that bad? I mentioned earlier this. So the underlying thing is that when we did that copy, every single file was being scanned every single time. And because it was serial I/O, that was how we got a minute from it, just by going and copying it across. I think it was only a minute because Defender probably has a cache for the hash of the file, and it ended up just being a hash of the file or something like that. I don't have any insight into that. I'm just speculating. But, you know, I wasn't really happy at this point. I'd spent a bunch of time making this better. I still hadn't worked on my Rust project, and it wasn't as fast as Linux. And I don't know about you, but I can't read 20,000 documents in 11 seconds. I can't read all of rustup's documentation in the time it takes to install, so why is Defender bothering to scan it for me? That's the only reason to scan something, to be able to use it immediately. I'd like it to not scan it and to do something with that later. So I started trying to find if there was some way to get Defender to behave better. It turns out that Steve Klabnik, for whatever silly reason, followed me. And he knows someone at Microsoft who turns out is a product manager with the right connections. And the really interesting thing was, oops, one too far. This response ruffled some feathers. I got nasty grams. Not many, but yeah. So I'll talk more about that later. Now is later. The discussion that we ended up having with Microsoft was really excellent. Like, they're obviously developers like you and I. They're there doing their job, trying to fix a thing, and they probably don't interact with the wider community using their product directly all that often. So it was kind of weird having this direct conversation with them. The basic thing that they asked for was ways to either reproduce it, but also they have this feedback hub, which essentially is an automated dtrace system where you run the thing, it generates a trace and sends it into their system, and you get an ID back. And you can either stop at that point and hope that somebody looks at it, or you can put that ID into a bug tracker that they're looking at, and then they will look at it and you'll get some actual attention looked at it. So once we'd kind of established that what we were trying to do wasn't silly or insane and that it was important to them, which took a little bit of time, they moved relatively quickly and made things happen. So I'm only going to talk just a little bit about this. The normal path that you see is you do close handle, scanning takes place, and you get an IO or an error back. And once we did this threaded thing on my 64 thread Threadripper 2 workstation at home, because I got back home from my road trip at this point, I was throwing close handles latencies up in the many tens of milliseconds, not nanoseconds, tens of milliseconds for a syscall. If we dispatch work to Defender faster than the scanning engine is going to take care of it, it's going to back up, and your syscall latency goes. The other thing that happens, though, in the antivirus world is that you reboot a machine, and once you've rebooted the machine, everything is suspect. So you've got to have another path. Open, scan, and then get an OK or error. So the question becomes, how can you get the files you've written to be treated as though you've just started the machine up? Don't scan them as I write them. Let them be scanned when they go to be read. And there is a mechanism in the antivirus database that's pushed out over the web to make that happen. But there's no API where you can say, hey, I know that this is appropriate for me, which is a shame. Took a couple of weeks to get it all sorted out, and then after that, rustup overheads went off a cliff. Suddenly, the performance overhead went away. It's like, boom. All of the other stuff I'd done, because remember, right at the beginning, turn Defender off, still slow. So now, what we've done is we've made it so that even with Defender, it was reasonably fast. It was about 11 seconds. Now, you turn Defender off, and it was 4 seconds. So, sorry, we'd made it so that with Defender on, it was about 11 seconds, and now they did this thing that made Defender not be an overhead, and it dropped down to equal with Linux. So I was like, okay, job done. I'm really, really happy. Did suggest that they should have this API, because there's other projects, Git and HG, Make, BZR, things like that. Anyway, of course, there was some fallout. We had to make it slower when it fails, because McAfee. And I don't want to name names, but McAfee. But also NFS. It turns out that folk using NFS servers had problems. We posted on Reddit that we'd made rustup a lot better, and maybe people would like to give it a go. And one of our users came back and said, it's really terrible in our supercomputing cluster. Come and have a look at it. And so we dug up some stuff on Lustre, which he said was the file system he was using, and he went and tried it. And he came back and told us that all the commands were failing because his home directory was actually NFS. And so we dug into that. First thing, okay, we didn't close handle in a thread, but we hadn't moved close over because I was conservative, like we don't want to destabilize everything. Narrator. This did not solve the problem. Get some trace information, syscall latency, open at 3 milliseconds, fchmod 2 milliseconds, chmod 1 millisecond. Earlier I said we did the separate pass where we set permissions. We extract, and then later we went and set permissions. Now this was to fix up bugs in the way things have been tarred up in ancient history and Rust's thing. But when you add these up for 20,000 items, that 1 millisecond time becomes 20 seconds, 2 milliseconds is 40, and 3 milliseconds is 60. So that's 120 seconds just in syscall overheads there. So this led to a rather larger patch set. Thread all the file I.O. Write a thing to thread directory operations, keep track of the file I.O. that you can't dispatch yet, and when the directory completes, dispatch all of that file I.O. all at once. And when you're at it, apply that fix-up logic at the same time as you're doing the file I.O. for the files. So we're no longer writing, making, chmodding in the main thread. Now the main thread is just extracting, and everything is taking place in these one worker thread per CPU, which isn't necessarily the right heuristic. At this point, I also took the time to put in a tracing system that outputs Catapult trace files. Now, Catapult is the project behind the Chromium in-browser profiler. So you can load that up into Chromium, and it looks like you've got a browser performance trace, but actually it's showing you the Rustup performance. And it's a generic Rust module, so you can use it for other Rust projects as well. I didn't write it. It's just like a really cool project. Go and grab it, use it. It's great. And that got us down to 15 seconds on that NFS server. I think we could probably do better, but it would require a bit more work and effort. So I was reasonably happy with that. So lessons learnt or rediscovered for the, what year are we? Time?
The best year for hindsight.
The best year for hindsight, 2020. Syscalls are not free. They're not free on Linux. They're not free on Windows. And don't blame a bad performing program's serial code, serial performance on NTFS or anything else. And if you've got antivirus in there, it's going to make everything look worse, not because it's the cause of the problem, but because it's doing its job. Of course, at this point, I was like, hang on, there's another Unix-like environment that we haven't looked at. I wonder, we've done all this work. Any guesses? All right. Well, the first thing was that the process name's different, so Defender didn't pick it up. So, all right, so that was relatively easy. I knew exactly who to talk to about that. But even when I didn't wait for them, I just disabled Defender and, yeah, okay. Turns out open got slow. Close is slow. No, open is slow? I wonder. There's a bug there that's been open for a while. And this is another bug where there's been an awful lot of discussion, but the rigor in the analysis, yeah. Platforms include tools for analyzing the behavior of programs running on them. Windows is the same as any other platform in this regard. You can get very, very deep into what's going on. Process Monitor, the new tracing toolkit, whose name I forget, and complaining about the performance of a thing by running a high-level thing like a kernel build or an npm install without digging all the way down to understand exactly what's going on doesn't advance a bug report. All it does is show that you understand that it's still slow. End of rant. So about 20 years ago, nearly 20 years ago, before VMs, when you wanted a Linux environment but still had to work in corporate environments, there was another option. Does anyone remember this other option? Ah, yeah. So to work on Squid back then, before I worked for Canonical, I started contributing to, and eventually became a core contributor on the Cygwin project. Just on the community side, I didn't work for Red Hat. So WSL 1 is very, very familiar territory for me. I've got a pretty good idea about exactly what's in that code base. I haven't disassembled it. There are EULAs and stuff involved, but I know what it's got to do. I know the challenges that are involved. Its mandate is more specific than Cygwin's. It's aiming at binary compatibility with the data structures and the ABIs, but it's not a fundamentally different challenge. It is quite a hard challenge. Anyway, hi Chris and Kawina from the Cygwin project. We're back doing the same stuff again. So a trace analysis inside WSL and at the same time a process monitor trace of the same activity outside lets us correlate exactly what's going on. And this is a little hard to read on the screen, but there are 3 threads. So you've got the timestamp and the thread number. The first thread starts a close on a file descriptor. A second thread starts an open at. A third thread, so the second thread completes its create file on the NTFS side. It's finished. Doesn't have any more work to do. It should be able to allocate a file descriptor number at this point. Then a third thread starts a close on another file descriptor, and then the first thread completes its close on file descriptor 8, the first file descriptor that we saw being actioned in this snippet. And then finally, the file descriptor that was doing an open completes its open. This smells like a course lock to me. I don't have the source code, but maybe we can just confirm this by checking that, in fact, the file descriptor that was slow had a slow syscall on the NTFS side, and maybe that Defender was involved, which would sort of tie everything together. That our close handle latency drove everything. So let's have a look. The file descriptor 8, when we track it back, turns up to be an HTML file. So it needs this high degree of engine processing, and you can see the timestamps there, and that's the open. So the open's fast. And then down here, you can see the 12 millisecond, which is extraordinarily slow for a close file call. And this is the Defender engine.
I think your slides.
Wrong one. All right, it's not bringing my mouse over. My mouse is on the wrong side, isn't it? There we go. All right, so this is the open, which is completely fine. It's about a millisecond. It's not super fast, but it's tolerable. I'd look into that once I made things not terrible. And this is the, terrible is a very harsh word to use. I shouldn't use it, I'm sorry. This is a 12 millisecond close file, which is driven entirely by the Defender engine doing a file mapping and so on. So it's setting up a mmap so it can scan the file content. So when that finishes, then the close file call, which is blocked. We can't see the thing, but it's inside the Defender engine filter driver layer. Releases and everything unwinds and it completes. So, yeah, I let Microsoft know that I've done some analysis and they might be interested in it, but I haven't got any concrete information back from it at this point. But the key thing is, it's not NTFS. It's not the Unix code at this point. At this point, I think it's the WSL v1. I've got some thoughts on the WSL v1, but that is another separate talk. And I have 3 minutes or so for questions, I think. Yep. Yeah. At this point, please. Yeah.
Forgive me if the question's a bit silly, but I thought the reason for doing a malware scan on a write rather than waiting for the open is so that you know when the malware arrived on your machine, not just when it tries to do bad things. So if a program can just tell the antivirus engine, hey, don't scan this when I write it, it's kind of working around that. How is that possible with an AV product?
Well, you can just record the time that the file was written and capture that in a log without doing any complex processing. I mean, that would solve the use case without this big delay. I've got one over. Yep. So, let's optimize for speed here. And there's 2 behind you when he's finished.
What was the context of the nasty grams that you got when Microsoft helpfully started replying to you?
I think it's probably best summarized as, we are all suffered from this pain. Why do you get privileged access to get help from this huge company? And I think the answer would be, I asked nicely.
Jesus Christ.
So, I mean, honestly, everyone is human. If you want to have a good relationship with people, coming in with all guns blazing about how something is terrible is absolutely not the way to make it work. I had my facts in a row. I'd clearly done a bunch of work. I asked politely, and I have not gone on. I mean, even in this talk, I think I've been pretty clear and respectful about everything that's going on. I could easily imagine a version of this talk which would be presented in a completely different way, and if I did that, I don't think I'd still have a relationship with Microsoft, and I wouldn't do that because I don't think it's professional.
Hi. Have you ever tried with WSL version 2?
So that's a very interesting question. You need to be on inside a ring build of Windows, and I haven't done that at this point. I have seen some bug reports talking about performance deltas. Obviously inside the hypervisor it's completely fine, but the Plan 9 interop, I think that's probably still pre-release, and so any performance numbers are going to be up in the air. I'm very interested to see what the release version looks like. And until then, I'd suggest have a look in the WSL bug tracker. If you search for WSL v2, there are some very interesting bugs to look at.
Yeah, so async is, of course, the new hotness in Rust. Would that
Excellent.
programming model have helped, hindered, made no difference here? How might that have made difference?
There's no, so the key thing is that the thread gets blocked. So would async as a way to represent this code have made the code a bit easier to write? Perhaps. If you go and look at the code, you'll see we have things like a resource tracker to track how much memory footprint we're using at a particular point in time, which would need to find, would need to still manage that. There's no async at the kernel layer, async version of close handle. So we'd still have to actually use a real thread, and we'd have to have an executor that's going to go and use a thread, and we'd have to scale that out, and all of that machinery would still have to exist. It might be a bit easier to read, but the parallel library we're using is pretty compact and nice to read anyway.
Thanks for that. So it seems like my takeaway personally from this talk is if other projects like NPM and Yarn wanted to also improve their performance problems that they have, the only solution is to be extremely fastidious with every single aspect about it. Is that a fair takeaway? So someone needs to be as diligent as you were with all of those other projects?
Yeah, no, absolutely. There's no magic bullet.
One last question.
So would you say that really the problem here is that the entire operation was all serialized, and as soon as you threw that into a worker pool, then you could essentially parallelize it? Because even if you could think of the open, write, close sequence, if this entire sequence was just thrown into a worker thread, and then you could just move on and just essentially saturate the thread pool, then essentially you would be doing the same thing. So would that be a default strategy? Is like, our code is slow, just throw it into a thread pool and move on?
So that's a good way to throw more concurrent load at the underlying components in the system. They can then saturate themselves, and you need to work to make sure you don't over commit or create issues. So for example, like I just mentioned to Gus, we have to track the amount of memory footprint we use. There are some users who have very large machines, like 128 core, gigabyte, well, probably terabyte machines, but the per user U limits are set very low. So when they run rustup on this, it tries to create a thread for every core and promptly runs out of memory. Because as it dispatches I/O off to every thread, the sum of the outstanding memory exceeds the memory that the user's been allocated. So if you're trying to make something faster, finding places where you can get parallelism and using pools to do that, yes, absolutely. But then look at the other constraints that are going to bear on that and make sure you don't exceed them.
I mean, as long as the pool can work. Thank you. I mean, if you simply have an executor pool, like I guess in Go, then as long as that executor pool, because it's limited in size and the memory is allocated at the start and it's just running, then you know you're not going to essentially have unbound growth. So you know that pool is going to work, and it's just a matter of, are you going to saturate all the workers, you know, with your load, right?
More or less. It gets, like, performance analysis is a long feedback, look, experiment, try, repeat. There are multiple strategies for getting good performance out of things, and you just need to keep going back and looking at what your results are and evolving.
Okay, please give Robert a big round of applause.